anytime you're working with a log equation, you're going to, most of the time, and I would say 99% of the time, you're going to rewrite as an exponential. So I have the log of something equaling a number. That means 3 raised to the 1 power is equal to the argument, so that x minus 4 equals 3 to the 1, or x equals 7. That problem looks familiar. I was working on the review and your final. Review for Monday and your final. I think I've seen that problem or something similar before. And not your final, your test. Now here's going to be a key here. When you're working with this, I don't see a base, but there is a base. What is the base? 10. So you rewrite this as log base 10 of 5x plus 2 equals negative 0.25. Now 10 to the negative 0.25 is equal to the argument. So 5x plus 2 equals 10 to the negative 0.25. Now what I personally would probably do, and see what 10 to the negative 0.25 looks like. I would probably do 3 decimal places, 0.562. That makes it easier to work with. So 5x plus 2 equals actually it's approximately 0.562. Now that makes that easy to work with. So that 5x equals, now I'm going to subtract 2 from both sides. So subtract 2 is going to be negative 1.438. Now I'm rounding each time, so every time I round, I'm bringing in round-off error. Divide both sides by 5, so that x equals, now divide by 5, negative 0.288. So this is approximately negative 0.288. So once I went from here to here rounding, I introduced error. Once I go from here to here rounding, I introduced error. And so at which point, if I go to check this, it's not going to be exact. So it says that the log of, and that's on my calculator, 5x plus 2 should be equal to negative 0.25. So if I wanted to do a check, is it true that the log of 5 times negative 0.288 plus 2, is that equal to negative 0.25? Let's see how close we get. Because that's base 10, that's on my calculator. So I can take the log of 5 times negative 0.288 plus 2. And it says, is it negative 0.25? Close. But you see, 181, all of this here from the end here on, that's round off here. Now, if you're an engineer building a bridge, that might be enough for the bridge to fall down. Which means that you would want much more accuracy. But for us in a math class, close enough. When we're good, we're very, very good.
squared is?
This is going to be the harder of the logarithm problems because of the fact that what we're doing is using the properties of logs. What you notice is when we have it in this format, in other words, a single log on one side, a number on the other, we can rewrite it, and that's how we solve these suckers. But if you take a look at it, I've got a log added to a log equaling a number. I can't rewrite it at that point. So what you do is you use the properties of logs to bring it together. So if I have the log of x plus the log of x minus 3, properties of logarithm says it's the log of x times x minus 3 equal 1. Now this guy looks like the ones that we worked previously. You can rewrite it into exponential notation, so x times x minus 3 is equal to 10 to the 1. Now I've got a quadratic, and then you factor and solve. Now the biggest thing you're going to have to do is to check your answer, and it says I can't take the log of a negative number, so if x is negative 2, I'd have the log of negative 2, and I can't take the log of negative 2. So this guy is not going to work. That's the only thing you have to do, to take your answer up and see if it makes either argument negative. If it does, toss it. It's kind of like we did with the radicals, where we couldn't take the square root of a negative number, and we had to go back up and check to see if it made the radicand negative. It's the same kind of idea.